So we'll look at a class of spaces, Eilenberg-MacLane spaces, which we implicitly saw just now. Key point about this is their homotopy type is determined completely by their fundamental group. And the goal is to see these things. And they include many familiar spaces. So it's not as if we have constructed a space which has some nice properties, so we say here it is, but existing spaces will often have these nice properties, and they're useful in many other ways. So let's just, so these are define them. So these are just X is a CW complex. By the way, often implicitly I'm assuming non-empty, okay, and with the following property that so it's path connected, and all higher homotopy groups vanish. So this is 0 for all n greater than or equal to 2. And as we saw last time, equivalently, X tilde, the universal cover of X, is contractible. So it's a CW complex whose universal cover is contractible. We have seen examples of these. Example is of course circle, as well as torus, which is S1 cross S1, and indeed the 3 torus and anything else, product of such spaces. We have also seen but not proved surfaces have these properties. So we have seen it. So there are many familiar spaces that have these properties. Okay. So as I said, we will see how their homotopy theory is determined by the fundamental group. Let's first start with one such theorem. So suppose we take Y is a CW complex. Okay. And X Eilenberg-MacLane space. But this is a bit long to write, so we'll also call them KG1. Okay, so classifying spaces. G is going to be the pi1 of X with X some base point. And 1 stands for the fact that this is pi1. So they're called classifying spaces, KG1s or K pi1s if you call this group G. Okay, so you take Y as a CW complex and an Eilenberg-MacLane space. And so suppose we have, and let me take Y0 as a CW complex, and we can throw in the base point X0. So given a map phi between fundamental groups to X60, okay, there exists F at the level of spaces. So given a homomorphism on fundamental groups, there is a map between spaces to X60 such that phi equals F star. Our next theorem will tell us that this is actually even unique up to homotopy. So that's what would justify saying that things are determined by these. But first of all, this is saying, so this is sort of, it has to go to pi1 of y0. This is kind of reversing what you have with a functor. So you say the functor is, in this case, surjective. Okay? So if the target is an Eilenberg-MacLane space, any map is induced by a map on fundamental groups. So we'll work inductively, but because pi1 is non-abelian, things always get a little more complicated there. So we'll really inductively define, not on pi0, but on y1, sorry, not on y0 straight away, y1, y2, etc. Okay, and y1 will involve this maximal tree. Okay, so let T. So y1, remember, is a graph. We have seen this before. So let T be a maximal tree in y1. So it includes in particular all the vertices of y1, tree in y1. So by the way, to have this maximal tree, I'm going to assume this is path connected. Formally, many things will be true anyway. In fact, the statement will be true just by taking the path component. But let's take, assume it's path connected. Let's take a maximal tree in y1. Okay. And let's first of all define, we'll keep calling the map F, but we'll say with a restriction to this. F restricted to T from T to the space X by sending everything by F restricted 2 of X to the base point X0. So it's a little confusing if I call this x, let's call it y. F restricted to of y is x0. Okay. Now let's pick an edge which is not in the maximal tree. So here we have a maximal tree, and here we have an edge. Okay, and let's call it E, and we want to define it on this. Now remember, there is unique up to homotopy, or you want to make it really canonical, you can take a reduced path. Paths joining E to the base point, y0. Okay, and so these give you hence elements in the fundamental group. Any edge E, so this is going to be, so an edge here is a one cell E, not in T. So unlike the case of our graphs, they don't come in pairs. We have chosen an orientation effectively. Not in T. So if you have any edge, gives an element in pi 1. So let's call it some theta E in pi 1 of the base, which is y0. Okay, and so this is in, so it gives it as follows. So theta E is going to be equal to, if I have given this point, so this is of course E of initial vertex of E, so but we can write it as E of 0, this is E of 1, and suppose the canonical reduced path is CV to any vertex V, so theta E is the class of, go from y0 to this, which is going to be C of E of 0 star E star C of E of 1 bar. Yeah, so you have this canonical loop, so it gives an element theta E. Okay, so then we have a map. We are given our homomorphism. Then phi of E belongs to pi 1 of x0. And by definition, this is going to be equal to lambda for a loop lambda. Mapping 0, 1 to x. Okay, but in fact lambda of 0 and 1 go to 0, and so I just write it loosely like this. 0 and 1 go to the base point x0. Because we map the entire tree to x0, we are in good shape. So we can simply define f of a point E comma s, something like that. So if I have a point E comma s, so now this is how we would do it in the case of graphs. Here we will want to instead write it formally slightly differently. We will define f on a one cell. So f restricted to, define f on D1, which is just 0, 1, by f of s is just going to be lambda of s. So on this one cell, and then this is consistent with the quotient. Okay, so so this is, and do this for each one cell. So do this for each one cell. Each E, which is not in the tree. Okay. So on each of the edges which are not in the tree, we extend the map from the boundary by looking at the image of the corresponding element in the fundamental group and taking a loop that represents that image. So this is our first major step. We have defined things on the one skeleton. Having done things correctly on the one skeleton, we'll see that the extensions are automatic. First to the two skeleton and then beyond that as well. So here and even earlier, though I did not say it clearly earlier, the fact that various extensions we are defining are continuous follows from the fact that it's a cell-weak topology. If it was a finite CW complex, it would just follow by gluing lemma. But otherwise, the compositions with the characteristic maps are more or less by construction continuous. So that's why our maps are going to be continuous, even if it's locally infinite. So before we actually extend to two cells, let's see what we have achieved here. We are when we constructed things rather carefully on the one skeleton, because the other cases will be automatic. But here, well, we had these curves mu e, let's call them, which were xi E of 0 star E star xi E of 1 bar, that is path from, so I had my base point y0, I have my maximal tree, and I have my curve not on it, and I took a path which went from y0 to the initial point. I have such a path defined for any vertex, and I could just take a path up to homotopy. I mean, take arbitrary path and say everything is well defined up to homotopy, but might as well take the reduced path. That's cleaner since we have such a canonical object. Okay, so we have these mu e, and what we achieved is, let's look at f star of mu e, the class of mu e. Okay, so now f star of mu e is of course the class of f composed with mu e, which is just the class of f composed with e. So the thing is that since the entire tree T gets mapped to the single point x0, this image actually goes to a loop, and a loop at x0, and the rest of it has collapsed to a point. So up to homotopy it's this class, but remember this was by construction phi of the element mu e. Okay, so but now mu e generate. So as mu e generate, what we see is that f composed with mu e, I'm sorry, we simply see that f star equals phi. Okay, now phi is a homomorphism. Okay, so something more specific we can look at, namely that if in particular, suppose we took a loop lambda. So lambda is a loop, omega of x, not x was the codomain in this case, y and y0, with lambda this homotopic to the identity, which is equivalent to saying that lambda extends to a disk. And here I look at lambda, here I'm looking at lambda as a map from circle to the, in fact, S1 with base point 1 to y0. Okay, so if we take lambda with which as a map extends to a disk, which means this is equivalent to E, this implies that f composed with lambda is equivalent to E. This is a different E, so which implies that f composed with lambda extends to a disk. Okay, and by change of base point, because change of base point is an isomorphism, by change of base point, what we see is that if, let me call it lambda from S1, and I don't need a base point, any base point, S1 to y extends to whatever I would want to call it, some capital lambda mapping D2 to y, so does f composed with lambda. Okay, so now we are set. Now we are set. So we want to define on the 2 skeleton y2. So remember, this is y1 disjoint union of the disjoint union of d alpha 2 by equivalence, and the equivalence relation is given by phi alpha, which maps S1 to the 1 skeleton. Okay, and on this f is defined. So all we need to see is that for any given cell, we have to be able to extend to the interior. So this is defined, and the boundary is already identified with a point on in y1, and hence what we have is the extension problem is for all alpha, and whatever this is A2 according to our notation. What we need to say is that for any such thing, if I look at F composed with phi alpha extends. So let's be explicit, since this is the important point. This is S1 to. Now the target X extends to whatever we want to call it. Let's keep it anonymous, but the map from D2 to X. Okay, so this is what we have to do for each alpha. And as I commented a few minutes ago, because of the weak topology, so if you do this, all characteristic compositions with characteristic maps are continuous, and it follows that the map is continuous as well. Okay, you don't, if it's locally finite, you could use the usual gluing lemma. Otherwise, you can't, because you'll have infinitely many closed sets. But you still can do it this way. Okay, fine, but we are done actually. We knew this, okay? But phi alpha mapping S1 to Y extends to a disk. Okay, that we saw already. Yeah, that's, I mean, it's simply the disk that we are filling in here. So what we have done is we have attached a disk. So the boundary map extends to a disk. Namely, we look at the identity map on the second component and then compose it with a quotient. Okay, and so what we claimed is above is using the change of base points and the fact that we had a homomorphism. Hence, F composed with phi alpha does. Okay, so this is it. We are done. Yeah, so what we want to say is that we can extend to the two skeleton. We'll also extend to higher skeleta. That is easy, and we will use more or less the same way. Okay, so what we do is we extend inductively to xn for n greater than or equal to 3, and if needed, take direct limit. That is to say, if we had. So direct limit is a rather simple thing in this case. We want to define a map on all the cells. We have already defined it on the cells. So it's a union in some sense of the maps. That's a particularly simple version, but it is the direct limit of maps. And again, by weak topology, this would be continuous. So how do we extend inductively? So at each stage, yeah, so we have to define. So let's write it. Xn is going to be xn minus 1 disjoint union of not d alphas, but disjoint union of the disjoint union of alpha in an of dn, which we can call dn alpha, and we quotient it, okay, with f defined on xn minus 1, and to be explicit this time, hence on boundary of d alpha n by f composed with phi alpha. Here this f is the previous thing, so this is really f instead of saying it's equal to, this is f restricted to xn minus 1 composed with phi alpha. Okay, so it's already defined on these. Okay, so we can extend f restricted to boundary d alpha n, which is Sn minus 1, and n minus 1 is greater than or equal to 2, to d alpha n. Well, this was just our hypothesis, as pi n of what was our target space called X is trivial. Okay, at this point I apologize, I have to make corrections here. This was a not subtle point, so it's not so serious, but you may have spotted that actually our domain spaces are all Y, not X. It's not the target space that we are doing, but this was not delicate. So we can see that as, but here really we are using of pi n of x, x0 is 0. So we are extending across all disks, and because the target space has is an Eilenberg-MacLean space, all its higher homotopy groups become 0. As a result of that, you can extend any map from d alpha n to pi n of, sorry, we can extend any map from the boundary of d alpha n to d alpha n, okay, and hence we can define it on the k-skeleton. This completes our argument. Okay, we will now see a complementary result which will tell you that this extension is essentially unique. Again, that will involve subtleties only in these dimensions 1 and 2 as well. And we'll again need to use our tree and our loop zetas, etc.